along with the awareness of the world community to reduce greenhouse gas emissions, which also coincides with a decrease in the average world oil reserves, then a change towards the use of biofuels is the most logical step. The problem is that biofuels, which are widely available in the market today, still contain quite high oxygen concentrations. This oxygen concentration, in addition to reducing the energy density of these biofuels, is also have more serious impact on engine performance, requiring different treatments since it is produced, stored, distributed until sold at point of sale to consumers. As a result, the infrastructure costs to enlarge the current portion of biofuels will be very high if the biofuels that are commonly used today, such as ethanol and biodiesel, are used. From here, since several years ago the International Energy Agency, IEA, introduced the concept of drop-in biofuels, namely liquid bio-hydrocarbons that are functionally equivalent to petroleum fuels and are fully compatible with existing petroleum infrastructure. From this graph, we can see that the main challenge for converting biofuels into drop-in biofuels is how to remove oxygen, which is very useful for our lives, but its existence is undesirable in the drop-in biofuels. The process of taking oxygen out from the hydroxyl functional groups, esters and ethers, is generally called deoxygenation. Then what kind of raw materials are needed that can be processed into drop-in biofuels? In general, almost all biomass can be processed into drop-in biofuels. It's just that the need for additional materials, especially hydrogen in the processing stages, will differ from one material to another. The higher the effective ratio between the hydrogen and carbon of a feedstock, the less need for additional materials in the steps involved in producing these drop-in biofuels, and vice versa. Drop-in biofuels have an effective ratio of hydrogen and carbon of 2, which is the same ratio as that of common hydrocarbon fuels. Then the basic raw materials that already have a ratio close to 2 are certainly easier to process into drop-in biofuels. For example, vegetable oil and animal fat. The ratio is already 1.8, so it can be directly processed into drop-in biofuels, with what is called the oleochemical process. Lignin, which has a ratio of 0.6, and lignocellulose with a ratio of 0.2, can also be processed into drop-in biofuels, but it requires a lot of additional materials in the form of hydrogen and a long process, which is called the thermochemical process. Likewise, sugar, which has a 0 ratio, can become a drop-in biofuels if it is carried out in an even longer process, through what is called a biochemical process. Due to very basic technical considerations, namely the oxygen-to-carbon ratio and the hydrogen-to-carbon effective ratio previously described, we highly recommend tomato oil as a raw material to be developed for our mainstay of drop-in biofuels in the future, replacing our hydrocarbon fuels, which are indeed going to run out soon, and our concern for carbon emissions, which should be suppressed as much as possible. In addition, tomato trees can be planted in critical and very critical lands so that they do not fight over agricultural land and forests. Tomato oil is non-edible, so it doesn't fight over with food. This program is carried out by New Energy Asia in synergy with Green Wakov,